Welcome to class number 9. In this class, we will learn about sensors that are based on polymeric nanostructures. We will start first with reviewing the main properties of the polymeric nanostructures, as well as with their advantages in the field of sensors. A polymer is a compound that consists of repeating structural units and that is created by polymerization process. Nanostructured conducting polymers exhibit certain unique properties that makes them advantageous over their bulk counterparts in certain types of applications. Nanostructured conducting polymers can be excellent complement to an organic conductor since they possess certain highly desirable characteristics, which include, amongst the rest, simple tunability over their band gap, high mechanical flexibility, greater biocompatibility than many inorganic materials, and low fabrication costs and simple processing techniques. Also, nanostructures that are made from polymers might have infinite variety of structures that can be utilized for a wide variety of applications. There are various possible nanostructures when working with polymers. Here are some examples of polymeric nanostructures. The first structure is called nanofiber. Nanofibers are defined as fibers with diameters less than 100 nanometer. An example of polymer-based nanofiber is shown in the uplift image. This scanning electron microscope image shows that an ensemble of nanofibers of polyacrylonitrile, or abbreviated as PAN, produces a large fiber that have a diameter of 3 micrometer. This fiber is produced by near-field electrospinning. The second structure is called nanorod. Nanorods are morphology of nanoscale objects in which each of their dimensions range from 1 to 100 nanometer. Standard aspect ratios, namely the ratio between the length and the characteristic width, or the diameter, in nanorods are between 3 to 5. In the middle image of the top row on the screen, you can see an SEM image of nanorod arrays that have vertical alignment. These nanorods have been shown to serve as ferroelectric sensors that have great potential in the organic electronics and energy storage applications. A third structure of the polymers is called nanotube. As we have learned in the previous classes, a nanotube is a nanometer scale tube-like structure. An example of polymeric nanotubes is seen in the left image of the bottom row. In this figure, you can see vertically well-aligned conducting nanotubes. And just to note, these nanotubes were created by aligning tens of thousands of very simple peptides comprising 2 amino acids. The fourth structures of these polymers is called nanoplates. A nanoplate stands for a nanoscale plate, and a rectangular coordination polymer nanoplates can be seen in the same image in the middle image of the bottom row on the screen. One of the exciting applications of these polymeric nanoplates is a fluorescent sensing platform for DNA detection, which has, by far, various applications in gene expression profiling, clinical disease diagnostics and treatment, fast detection of biological warfare agents, and forensic applications. The fifth and the final structures in this slide is called nanosphere. Polymeric nanospheres have the ability to temporarily mimic the growing environment of living cells. The polymer acts as a carrier, taking the cells deep within the damaged tissue throughout injections. These polymers can do their job effectively because they are very porous. This ability actually allows for nutrient chemicals to pass throughout and reach the cells that are stored within the nanosphere. Once at these locations, the polymer would be biodegraded, leaving the healthy cells inside the wounds. A sim image of the polymeric nanosphere structure is seen in the right side of the bottom row. One of the most important properties of the polymeric nanostructures when sensing applications are targeted is their electrical conductivity. We will discuss now these properties, and we will present such properties in the next sessions of class number 9. Conducting polymers have an alternating single and double carbon-carbon bonds along the polymeric chains. The highly conjugating polymer chain can be assigned reversible chemical, physical, and electrochemical properties, which can be controlled by doping and de-doping process, or usually we call it redox reactions. Conducting polymer nanostructures not only retain these unique properties, but also have the characteristics of nanomaterials, which further increases the merit of conducting polymers in designing and making novel sensors. Due to their outstanding optical and electrical properties, they have shown the promising applications in organic light-emitting diodes, photovoltaic cells, sensors, field effect transistors, and so on. Different properties of the conductive polymers can be controlled with the process called doping, namely, conversion of organic polymer from the state of either insulator or semiconductor to metallic state. Both doping and undoping processes involving dopant counterions which stabilize the doped state may be carried out chemically or electrochemically. So far, there are several types of doping. The first type of doping is redox doping. This type of doping involves the partial addition or removal of electrons to or from the p system of the polymer backbone. The second type of the doping is p-doping. This type of doping relies in partial oxidation of the pi backbone of an organic polymer with an oxidizing agent, or which we call it usually dopant ion. The third type of the doping is n-doping. This type of doping relies on partial reduction of the backbone pi system of an organic polymer. In each case, counter-dopant ions are introduced, something that stabilizes the charge on the polymer backbone. The fourth type of doping relies on photo-doping. So far, this type of doping occurs when the polymer is exposed to radiation of energy greater than its band gap, something that in turn leads to promoting electrons across the gap. The last type of doping relies on the so-called charge injection. This type of doping is carried out using a configuration of metal and conducting polymer separated by a thin layer of high dielectric strength insulator. Applying appropriate potential across the structure causes the resulting charges in the polymer. The current slide presents a plot of energy densities versus power densities for various devices. Closed circles represent data from the p-dot nanotube-based supercapacitor. The p-dot nanotube is a good candidate for a supercapacitor that provides high power density without significant loss of its energy density. This brings many advantages for the use of polymeric nanostructures, including but not confined to the following advantages. The first advantage is that polymeric nanostructures have an ability to reversibly change color under applied potential, something that have high potential in Windows, electronic paper, and bendable display applications. The second advantage is that polymeric nanostructures can be placed on flexible supports. The third advantage is that polymeric nanostructures possess higher power densities. The fourth advantage is that polymeric nanostructures exhibit enhanced charged or discharge rates. The fifth disadvantage is that polymeric nanostructures exhibit higher capacitance values. And the sixth advantage is that polymer structures can be used as supercapacitors or batteries. Further advantages of the polymer nanostructures include nanowire morphologies results in relatively high field effect mobilities. Polymeric nanostructures possess high on-off ratio of the pertinent field effect transistor devices, and polymeric nanostructures are able to create efficient charge transporters. An example of such advantages is shown in the presented figure on the screen. This figure shows current voltage curve of field effect transistor device based on P3HT film. Transistors with P3HT thin films possessing nanowire morphologies results in relatively high field effect mobilities that are approximately an order of magnitude higher than those of the same material, thin films, but without nanowire morphology. As a result, these materials should be superior to their conventional counterparts in field effect transistors and in other devices that require higher charge carriers. Additional advantages of the polymeric nanostructures is that conjugating nanostructured polymers would be their heat transfer properties. In general, conjugating polymers are strong light-absorbing materials in the visible region due to the low-energy pi-pi transitions. When exposed to light, conjugating polymers can convert most of the absorbed energy into heat. For bulk films, the generated heat can be rapidly dissipated throughout the material. However, the heat generated in nanostructured materials will be confined to within individual nanostructures because the heat transfer to the environment and the neighboring nanostructures is slow. This actually leads to a peculiar photothermal effect that is not observed in bulk materials, especially when a strong pulsed light source is used, such as the flash from the ordinary camera, which we use in our daily life. When a film of polyaniline nanofibers is exposed to a camera flash at close proximity, a smooth and continuous film from organically random network of nanofibers is formed. Flash welding provides an easy and rapid way to create asymmetric films, which are potentially useful as separation membranes or actuators. The latter example has recently been demonstrated as shown in the figure on the screen. In more details, a monolithic actuator with over 720 degrees of curling from an original 2.5 centimeter length film can be completed within 20 seconds only. The curling results when a symmetric polyaniline film is exposed to an acid, which is basically a reversible process. This phenomenon is partially a result of different densities of the welded and unwelded sides. When the asymmetric film is exposed to acid, the nanofiber portion of the film expands as a result of charge repulsion of the anionic dopants. Because the welded side is much more dense and cross-linked, the entire film bends and coils towards the welded sides. We come now to the end of class number 9, session number 1. Thank you.